All right. Well, it's been many moons since I've narrated a PowerPoint, and it's to be honest just as awkward as I remember it being. As I sit here in my office and I stare at my monitor screen, I have, of course, all my various stuffed animals all arrayed before me in hopes of simulating that classroom environment, to try to make it feel a little less uncomfortable. Um, I'm not entirely sure that I've succeeded with that particular goal, but nonetheless, we're going to push on anyways. We've wrapped up talking about confidence intervals and hypothesis testing, statistical inference, and there was some diversity in what we did, but also there was a sort of common theme as well. And that common theme was all the confidence intervals, all the hypothesis tests were all centered around a single sample. The mean of a single sample, the proportion of a single sample, and all our examples we were working with one sample, or to put it another way, one variable. Now we're going to move on and we're going to extend that to kind of a more interesting, more practical, more useful situation where we're actually working with two samples. And this particular set of PowerPoints is going to be very big picture because we've really done a lot of the heavy lifting. There's not a lot of newness. It's the same basic ideas. I really gloss over the formulas. The formulas get increasingly cumbersome. And so rather than sort of bombard you with their shock and awe, I sort of leave them behind the scenes for the calculators. So the PowerPoint's going to be a little bit on the short side, but I'm really going to suggest that you spend a lot of time working on practice problems from the textbook. And of course, if you look at our syllabus, you should see those problems assigned to you. So a lot of the pressure as we kind of move towards the end of this class is starting to slowly shift from me to you. And we've done a lot of examples already, and so I want you to kind of try to extend those examples to what we're talking about here. Many times we're interested in comparing parameters from two separate populations. As just one example, we might ask the question, does the average salary differ for males versus females in a particular profession, within a particular state, maybe within a particular country, maybe just sort of overall males versus females? Is their average salary different, yes or no? It doesn't even have to be comparing averages, though. We could also compare proportions. This is sort of a classic problem in terms of pharmaceutical industry, in terms of biostatistics, any type of experimental study where maybe comparing medicine A to medicine B, maybe medicine A to, harkening back to chapter 1, maybe we're comparing medicine A to a placebo. We would have two different samples. We'd have a sample of patients taking our new experimental medicine, and we would have another sample of patients assigned to take the placebo. We have these sort of two groups that we're going to compare to one another, ideally with the hopes that our medicine is going to outperform the placebo group.
Now, I use that term sort of significantly different. We've been using that in chapter 6, right? What's the idea behind significantly different, right? Remember, right, if we took a sample of males and a sample of females and we compared their sample means, that even if they really did, right, if we lived in an equitable world where males and females on average made the same amount, even if that was sort of our underlying reality, if we took a sample of males and we took a sample of females, we would actually be surprised if their sample means were exactly the same, because there's a certain amount of sort of random happenstance that involves the sort of sampling process. And so if we'd be surprised, if it's rare, if it's unlikely that the sample means are going to be exactly the same, that's the same as saying that we sort of expect that one sample mean, maybe the males, maybe the females, is going to be at least a little bit higher than the other. And that alone does not necessarily contradict a hypothesis that that males and females are making the same amount of money. The idea of significantly different is trying to get at the idea about whether or not this difference in sample means is sort of so large, is so extreme, is so vast, that it is unlikely that this difference is occurring by sort of random chance or fluke sampling. Now, one consideration when we're comparing two groups or two samples, perhaps the first consideration that we need to kind of to settle, is whether this is an independent or dependent samples. Independent samples, not surprisingly, there's no relationship between any of the experimental units in one sample and those of the second sample, right? We would say that these two samples, or the people within these two samples, are independent of one another. There's no connection between those in the first sample and those in the second sample. That's called independent sampling. Dependent sampling. This is a situation where there is a relationship between experimental units in one sample and the next, right? There's a dependency there. The classic example of this is giving a sample of students a pre-test and then a post-test of some sort of knowledge, and then conducting some sort of hypothesis test to determine if scores have, quote, significantly improved or are significantly different, right? So I have sort of two samples. My first sample is really all the students' pre-tests. My second sample would be all the students' post-tests, right? These values, these numbers, in these two distinct samples are connected, right? Each pre-test in the first sample goes with a post-test in the second sample, right? They're connected by a single student. Other examples might be twin studies, right? Where you have a certain twin in one, maybe they're given a certain treatment, a different twin in another, they're given a certain set of treatment, but there is a relationship between the twins, even though they're in different samples and they're being given different treatments, right? They have this sort of genetic similarity. A couple rules of thumb. When the two samples have different sample sizes, that almost always means that they are independent samples. It could be that you just have missing information, so you want to be a little bit careful, right? It might be that you originally set up your study with 50 sets of twins. So you had 50 getting, say, treatment A and 50 getting treatment B, but one of the twins got sick, and so you ended up only having 49 in treatment B, right? There are violations of this rule. But in general, if you see the two samples have different sample sizes, that often means that they're independent. You can't really flip that. Just because samples have the same size doesn't mean that they have to be dependent samples. Most sort of experimental design techniques are geared around the idea of what we call balanced sampling. And regardless of whether it's dependent or independent, most research designs try to have at least roughly the same amount of experimental units in both samples to sort of make them more comparable.
Let's start by talking about dependent samples. It's kind of a cool example of mathematical reasoning or mathematical simplification. In this particular situation, what do? What we do is we compute the difference in values for our paired experimental units. So go into that classic pre-test, post-test. If our fictitious student Andrew got 60 on his pre-test and 70 on his post-test, we would say that his difference, the difference here is the post minus the pre, we would say his difference is 10. If instead he got a 55 on his post-test, that is the score went down, we would say the difference is minus 5. So he's going to have a positive score if his score went up, he's going to have a negative score if his score went down. And instead of two observations for Andrew, we're instead looking at that difference, and so we're sort of condensing that into a single observation for Andrew. And not just Andrew. We also do it for Bob and Cindy and Dan and Guillermo and Javier and everyone else. And for all of our experimental units, for all of our students, we condense their two scores into a single score. And now what have we done? Pretty cool, right? We've taken a complex problem, we've simplified it into the type of context we can already solve. Now we're down to a one sample problem. And what we can do is we could take these differences and we can just do a hypothesis test that we learned previously, and see whether or not this difference is equal to 0 or not equal to 0, right? Equal to 0 basically means that there's no difference between the pre and the post test. If there's no difference, right, then the mean would be 0. If the mean's other than 0, then that would mean that there is some sort of difference.
If we were to formally set up our hypotheses, we would set up our null hypothesis that mu sub d, that's the mean of the differences, is equal to 0, versus the alternative that mean is not equal to 0. We could also, of course, do one-sided alternative hypotheses, right? So if we wanted to see whether test scores improve, that would be equivalent to an alternative hypothesis of mu sub d is larger than or greater than 0. If for whatever reason, I can't imagine that we would realistically want to do this, but if for some reason we wanted to test whether test scores decreased, I don't know, maybe if it was a weight, maybe if we looked at everyone's weight before a diet and their weight after the diet, right, we would want to see a decrease in that, so we might test mu sub d is less than 0. So that more or less takes care of dependent sampling. So let's now move on to independent sampling. With two independent samples, we can do one of two cases, much like we could in Chapter 6. We can consider means or proportions. We can compare means of two independent samples or proportions of two independent samples, ultimately with the goal of saying whether one is sort of significantly different than the other. Now, the basic steps behind this process are the same, right? We generate test statistics. We use these test statistics to get p-values. We use these p-values to make decisions. However, the formula for these test statistics can get very cumbersome and very difficult to do by hand. And with that in mind, they are best done with calculators, particularly the TI-8384 calculator, which we'll talk about doing as we get closer to the end of this PowerPoint. A test of means would look like this. So if we wanted to test whether two different means are equal to one another, right? Whether the average salary of males is equal to the average salary of females, we would set up the null hypothesis is that mu sub 1 is equal to mu sub 2, right? Mu sub 1 might be the average salary of males, mu sub 2 might be the average salary of females. Versus the alternative hypothesis that they're not equal to one another, right? It's a very direct, straightforward, intuitive way of setting it up. However, it's often written a little bit differently in practice. We can take those exact same hypotheses and we could rewrite them, right? If I look at that mu1 equals mu2 and I subtract from both sides of that equation mu2, right, I still have a balanced equation. And what I now have is that second set of hypotheses. What I now have is that mu1 minus mu2 is equal to 0 versus the alternative hypothesis that mu1 minus mu2 is not equal to 0. Right? When I set it up this way, I can see that the test statistic, or at least the sort of foundation, the numerator of that test statistic, is going to be, right, if I want to approximate the true difference in population means, well, my best guess for the population salary of males is the sample mean salary of males. My best guess for the population mean salary for females, that's mu2, would be my sample mean salary for my sample of females. So if I wanted to estimate that, I would look at the difference in sample means, right? And I would want to see how close or how far those are from 0, right? If the sample means are very close to one another, that's indicative that likely the population means are close to each other. If the sample means are very far from one another, that's of course indicative that the population means are very far from one another. Now, in practice, we often do two-sided tests. Not just here, in terms of Chapter 6 too. In practice, most people do two-sided tests. But in reality, we always could do one-sided tests as well. That is, we could do an alternative hypothesis that the difference is less than 0 or that the difference is more than 0. kind of as we already discussed earlier.
It's really much like we've done hypothesis testing before. You're just instead of putting in, for example, one hypothesized proportion, you're putting in that 0. Instead of putting in one sample size, you have 2 sample sizes. Instead of 1 standard deviation, you have 2 standard deviations. So I'll kind of leave it to you to kind of go through some practice problems. And of course, if you have any problems at all, let me know. I do a little bit of an example towards the end of the PowerPoint to hopefully help out a little bit. But just kind of big picture, and again, paralleling what we've already seen, if we want to compare the means of 2 populations and the population standard deviations are known, then we go to that stats test menu. We're going to select 2 sample z test. Z because the population standard deviation is known. If instead the population standard deviation is unknown, we are going to use a t-test, so that's going to be 2 samp t-test. And if we're comparing proportions, then we're going to use 2 prop z test. It's still a z when we do a hypothesis test of proportions, but we have that prop in there because we're comparing proportions, not means. So again, I'm being a little stingy with the examples because I really want to ideally empower you. I really want to try to motivate you, perhaps even twist your arm, hey, sorry, to get that book, to dust it off, and to do the problems yourself. That's the way to learn it, not by watching and listening to me do the problems.
Now, what I might be more interested in you being able to do, and something that I think is kind of more interesting if you're reading other people's research papers, is being able to sort of exploit or utilize an equivalence that I don't believe we've discussed between confidence intervals from chapter 5 and two-sided hypothesis tests from chapter 6, right, the not equal to ones. For example, if a two-sided confidence interval, right, every confidence interval has a certain percent, and the percent has to sort of correspond to whichever alpha or significance level you want for your test. So if you're doing a 0.05 significance level test, you would do a 1 minus 0.05, or as I wrote, 1 minus alpha, which is a 95% confidence interval. So, right, so if your significance level is alpha, your confidence interval is always going to be 1 minus alpha. Often your alpha is 0.05, often your confidence intervals are 95%. It's not a coincidence, they go together. So if a 95% confidence interval for mu1 minus mu2 was found to be 1.3 to 5, then what we would basically do, what we would conclude based on that confidence interval, this is something that I would want you to know and could be important to know on a test, is that we would reject the null hypothesis, right? The null hypothesis being that difference in means is 0. Why do we reject it? Well, because 0 is not in that interval, right? That confidence interval is saying that we're 95% confident that sort of the true difference is between 1.3 and 5, right? 0 is nowhere in there. And so based on that, we're pretty confident it's not 0, right? We would reject the null hypothesis that it's equal to 0. On the other hand, if our confidence interval was -3 to 1, we would fail to reject the null hypothesis since 0 is inside that interval, right? If we said we're 95% confident that the difference in means is between -3 and 1, then we couldn't reject the null hypothesis that it's 0 because it actually is feasible that it could be 0, right? The value of 0 is within that confidence interval, so it's reasonable to assume that that might be the actual value, the actual difference in means. Similarly, right, it's not only means that we can compare, we can also compare proportions. We would set it up in pretty much the exact same way. Null hypothesis is that proportion 1 equals proportion 2, P1 equals P2. Alternative is often that they're not equal to, but we could do one-sided tests as well. And just like before, these could be rewritten. They could be rewritten as null hypothesis is P1 minus P2, and that equals 0. versus the alternative that P1 minus P2 does not equal 0. Also, just like before, we could do confidence intervals for the difference in proportions, and we could ultimately use this to make conclusions as to whether we think the two proportions are the same or not. So same basic idea. If 0 is in our confidence interval, we're going to fail to reject. If 0 is not in our confidence interval, we're going to reject the null hypothesis. Now here I'm going to do an example of a confidence interval for proportions, because this is something that you might be expected to do on a test. So here's an example. Let's say that some new medicine is created. It's created with the goal of helping us alleviate wheezing conditions. Wheezing is a terrible condition, especially if you're trying to narrate a PowerPoint. And we want to know if this new medicine is significantly different, maybe better, but we also want to allow and detect the possibility that it's worse than whatever pre-existing medicine is out there right now for wheezing conditions. We're going to give, right, if we were to do this in practice, we would have to test the medicine out. So we would test it out on 100 patients. Let's say we did that. We give it to 100 patients. And we find that it alleviates symptoms in 70% of our patients. We also want to compare to the old medicine, so we have to give the old medicine to 200 patients. And let's say that we do that and we find that it alleviates symptoms in 50% of these patients. Our ultimate goal is to build a 95% confidence interval for the true difference in proportions. Of course, if we figure that out, we can ultimately use that to also do a hypothesis test.
We can do this very easily in our TI-83, TI-84. Stat, because it's a stats class. Test, because it's useful on a test. Go down, 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 way downtown to 2 prop z int, because it's a z interval, and it's for 2 samples. It's for 2 proportions, and you just fill in the information. It's twice as much information as it was before. So instead of just an x, we have 2 x's. Instead of just 1 sample size, we have 2 sample sizes. We still just have a single confidence level, because we are building just a single interval for that difference. So our x1 is 70% of 100. Our x2 is 50% of 200. We put in our sample sizes. We put in our confidence level, and then we see the solution on the next slide.
Solution. We should get, if you typed all that in correctly, that the answer of the confidence interval is 0.08656 to 0.31344. What does this mean? It means that we are 95% confident that the true difference in proportions is between roughly 8.5% to roughly 31.5%. That is, this is the same as saying that we're 95% confident that the new medicine is between 8.5% and 31.5% better than the old medicine. Now note, since this interval does not include the value 0, we're also confident that the new medicine is better than the old medicine, right, at the 0.05 significance level. Since we did a 95% confidence interval, that corresponds to a 5% significance level.